lesson we'll be learning the addition rule and these trig identities. You were probably given these in class and you never really explained how they work or why they work. So that's what we're going to be doing this lesson. And so there's a couple of things I've set over here. So these are two parallel lines. The two white lines are parallel. This is triangle OCE. OCE is a right angled triangle with angle alpha, and OEB is also a right angled triangle with angle theta. So if this is theta, we know that this will be 90 minus theta, and this is 90, so the other one should be theta too. We can also determine the length of certain lines on this graph. So we know that CA, which is this line over here, or AC, whatever you want to say, call it. AC, let's set this to white or red. AC, the length of AC will be equals to, this is the opposite of the two angles down here, so you know it's going, and this is set to be 1. OC is set to be equals to 1. So AC should be equals to sine theta plus alpha. We can also say that this line CE, because we determined this angle to be theta, we can say that this line CE and this line with this angle alpha and this line being CO being 1, we can say that CE is equals to CE is equals to sine alpha. We can also pick apart the line OE. So OE, we can say OE, because this is the adjacent line to alpha, we can say OE is equals to cos alpha. So we found a few lines that we can determine the length of, and as we know, parallel lines like these, since these two are parallel, the white lines are parallel, the distance between the two lines is always constant. So the distance here and here will be the same because it's a parallel line. They never get any closer or any further. So we can also say that CAC, the line AC, is equals to the line BD. Okay, so now that we have these lines set, I would like to start and maybe find the length of this line DB so that we at least know the length of this line CA. So we could start by finding DE at least. So DE, with this angle being theta, DE is equals to, if this is theta, then it has to be the adjacent of theta. This is the hypotenuse. This of course will be a right angle triangle over here. So that would mean that DE is equal to the length of CE times the length of times sine cos theta. Cos theta. DE is equals to CE times cos theta. We already established that CE over here, CE is the same as this CE over here. So we can put sine theta into this equation and get an equation for DE. DE is equal to sine alpha times cos theta. And now let's try get EB. So EB, we already know that EB should be the hypotenuse, which is OE, times the sine of theta. So EB the hypotenuse is OB. Sorry, I forgot to put my magnitude signs. EB is sine, let me start with the hypotenuse, is OE rather, times sine theta. And we know that OE, which we determined up here, is cos theta. So we can replace cos theta into the equation. We get EB is equals to cos theta times, seems to be a problem. OE is equals to cos alpha, not cos theta. Cos alpha times sine theta. Now we know, because these two white lines are parallel, that DB should be equal to CA. And since we know DE already, and we know BE, these two, DE over here, and BE over here. We know these two lines, so we shall be able to know these two lines also. So let me write these two equations separately. So DE, we've established that it is sine theta alpha rather cos theta, and EB is equals to cos theta cos alpha. Sorry, I keep making this mistake. Sine theta. And we know DE plus EB should be equals to dB, and dB is equals to CA. So let's start by saying CA is equals to dB. Should probably have written these the other way around. And also dB is equals to dE plus EB. So we know that overall CA is equals to sine alpha cos theta plus cos alpha sine theta. And what did we say was CA at the beginning? Remember, CA, as we set it to be CA, which is the opposite of alpha and plus alpha plus theta, CA should be equals to, when this is equals to 1, CA should be equals to sine theta plus alpha. So sine theta plus alpha is equals to sine theta alpha cos theta plus cos alpha sine theta. And we have our trig identity over here. So we've proven that this is true. Most of the times it's better to write it this being here and this being here to avoid confusion when you're having negative angles. But basically, you can think about it, so it's better to write it like this: sine theta plus alpha is equals to sine theta cos alpha plus sine alpha cos theta. It's better to write it like this because when you think about negative angles, imagine putting a negative in place of a negative alpha in place of alpha. So we know that sine of negative angles is the negative of the positive angles. Let me write that down. We know that the sine negative alpha is equals to negative sine alpha. So what will happen is this whole term will change into a minus, and when you have cos of negative alpha, cos stays the same. It's not going to change. So cos of alpha is going to be the same thing. Maybe I could show why quickly. A unit circle over here. So let me draw a line from here to here. This should be make it a bit longer. There should be your unit circle with a length, and this line has length 1. That's basically the radius. So we know sine is defined to be the opposite, or rather, this is the y-axis, this is the x-axis. Sine is defined to be the x-coordinate, y-coordinate rather. Y-coordinate, this is alpha. This over here is equal to alpha. Sine is supposed to be the y-coordinate of this. So if you were to take negative alpha will be somewhere down there. So you can see that the sine of positive alpha and the sine of negative alpha, this is in the positive y, this is in the negative y. So the sine of positive alpha is going to be equals to the sine of, to the sine of negative alpha. Wait, sorry, let me restate that. The sine of alpha will be equals to negative of the sine of alpha, because sine of negative alpha is going to be negative of sine alpha. And now the reason cos stays the same is because you can see that the x-axis stays on the positive side. The x-axis is still positive, and so cos negative alpha will be equals to cos alpha. So if we were to find an equation for sine theta minus sine alpha, if we were to find sine theta minus alpha, it's going to be equals to sine theta cos minus alpha plus sine minus alpha cos theta. We know that sine minus alpha is minus sine alpha, so, and cos minus alpha stays the same, so we don't even have to worry about that. So we can finally get sine theta minus alpha is equals to sine theta. Cos minus alpha stays the same, so cos alpha doesn't really matter. And then this, because it's equals to negative sine alpha, this becomes minus, so minus sine alpha cos theta. So whenever you want to change the sign in here, you can change the sign here, but only if the equation was first written with sine theta cos alpha in front, because if you were to write it any other way, you'll have to change the sign in front. The sign in the middle stays the same, so it's generally better to write it in this format to avoid confusion when you're having negative angles. So I can get rid of all of this. We can now move on to proving the cos addition rule. So we've proved this, and we can now move on to proving this one. So we can start by saying that the cos theta plus alpha, theta plus alpha is equals to the adjacent of theta plus alpha will be equals to OA. So OA. So now we can also say that OA is equals to the OB minus AB. So OB minus AB. This over here minus this gives you OA. OA is also equals to CD. So OA is equals to OB minus CD. And remember, this is equals to cos theta plus alpha. Now, we can try to determine what CD is and what OB is, the whole thing down here. Immediately we can see that OB is equals to the hypotenuse, which is OE, times the cos, the cos of theta. So OB is equals to OE times cos theta. That's what OB is. We could find an expression for OE, an expression for OE. We can see that with this being 1, with OC being equals to 1, you can see that OE is equals to the cos of alpha. OE is equals to cos alpha. We can put this back into the equation and say therefore OB is equals to cos theta times cos alpha times cos theta. We have an expression for OB now. Let's try find an expression for CD. So CD over here, with this being theta, this is 90 minus theta, this has to be theta too. So CD will be equal to the hypotenuse CF times the sine of theta. So CD is the hypotenuse, which is CE times sine theta Let's try find an expression for CE, because we want to leave this in terms of cos and sine only. An expression for CE, we can see that CE is the opposite of alpha, and since this is equals to 1, this is equals to 1, we know that CE should be equals to sine alpha. So CE sine alpha. We can put this back into the equation and we get CD is equals to sine alpha times sine theta. And once again, we have a full expression for, now we have a full expression for OA, and OA is OB minus CD. Here we established that OB is equals to cos alpha cos theta cos alpha cos theta, and CD rather, CD is equals to sine alpha sine theta. And remember that this, we can now say, therefore, cos theta plus alpha is equals to OB minus CD. OB is cos alpha cos theta minus sine alpha sine theta. Let me center this properly. Now we have our expression for cos theta plus cos alpha. Again, it's better to write it in this format. You have it easier when you're thinking about negative angles. And as I explained earlier, this, when it's negative, this over here will become negative, and the negative and the negative will become positive. So we can say that cos theta minus alpha is equals to cos theta, cos alpha. These stay the same because cos of a negative angle is the same as cos of the positive angle. This becomes negative, 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 positive. So plus sine alpha sine theta. So this is for both. We've done both now. Alright, so the last thing I want to do is think about these in terms of complex numbers. So hopefully you have a good understanding of complex numbers, but if you don't, you can skip towards the end. This is not really as necessary, but I just think it's nice to think about these two identities and see how they will also play in the complex number plane. Hi, so I realized that the angle alpha in this video might be a bit confusing because I didn't extend the angle towards the x-axis. It's not supposed to be the angle made with z, it's supposed to be the angle made with the x-axis. And just to clear out any confusion, yeah, that's all that I wanted to add. So we know that whenever you multiply two complex numbers like w and z, the resulting complex number will be the same as adding up these two angles. And this is being kept in the unit circle. Normally, if it's not on the unit circle, you'd have to multiply the magnitudes too. But because this is on the unit circle, everything's equals to 1. All you have to do is just add the two angles. So let's say w is equals w times z is equals to x. We know w can be said as cos theta, or sorry, z can be said as cos theta. Z is equals to cos theta plus I sine theta, and w is equals to cos alpha plus I sine alpha. Wz should also be the addition of the angles. So we can say x is equals to cos theta plus alpha plus sine theta I sine theta plus alpha. That's what x is. So you can say cos theta plus alpha. Let me move this to the side a bit because I might need a bit more space. Okay, now we can say cos theta plus alpha plus I sine theta plus alpha is equals to, and let's put this into brackets, cos theta plus I sine theta multiplied by cos alpha plus I sine alpha. We can expand this out. When we're expanding this out, you have to remember for the last terms, I sine theta times I sine alpha, because I and I is equals to -1, because square root of -1 is defined to be I, so I squared should be -1. So one thing we can do is we can factorize out I over here, and we can bring the real terms, the real number terms together. So we can say cos theta cos alpha minus sine theta sine alpha, and then plus I into sine alpha cos theta plus sine theta cos alpha. So now remember, with this being the real term, it should be equals to the real term over here, and this imaginary term, the real imaginary part of this, should also be equals to this imaginary part. So with this we can say that cos theta plus alpha is equals to cos theta cos alpha minus sine theta sine alpha, and sine theta plus alpha is equals to sine alpha cos theta plus sine theta cos alpha. And there we go, we've proved the equation again, but now using complex numbers, and that's our final product.